Large language models store an impressive amount of factual knowledge in their parameters. But here's the fundamental tension. That knowledge is frozen at training time, opaque to inspection, and impossible to update without retraining. Ask a model about last week's election results, and it has no mechanism to know. Ask it to cite its sources, and it can only confabulate. This is the knowledge problem, and in 2020, Lewis et al. Proposed an elegant solution: Retrieval-Augmented Generation, or RAG, a hybrid architecture that combines the generative power of parametric models with the precision and updatability of an explicit retrieval mechanism. This paper, published at NeurIPS 2020, would go on to define how the entire field thinks about grounding language models in external knowledge. Let's break down exactly how it works. To understand RAG, you first need to understand the distinction between parametric and non-parametric memory. Parametric memory is knowledge encoded in a model's weights during training. Think of BART or T5. They compress the entire training corpus into fixed-size parameter tensors. This is powerful for generalization, but the knowledge is implicit, entangled across billions of parameters, and fundamentally static. Non-parametric memory, by contrast, is an explicit, indexed store of knowledge that can be queried at inference time. Think of a search engine, a database, or a vector index. The knowledge is transparent, updatable, and inspectable. The insight of this paper is deceptively simple. Take a pre-trained seek-to-seek model as your parametric memory, take a dense vector index of Wikipedia as your non-parametric memory, and learn to combine them end-to-end. The parametric component, BART large with 400 million parameters, handles language understanding and generation. The non-parametric component, a face index over 21 million Wikipedia passages, provides grounded, retrievable facts. Let's walk through the architecture in detail. RAG has two main components. First, the retriever. This is based on Dense Passage Retriever, or DPR, which uses a bi-encoder architecture. You have two BERT base models, a query encoder that maps the input X to a dense vector Q of X, and a document encoder that maps each passage Z to a dense vector D of Z. The retrieval probability is proportional to the exponentiated inner product of these vectors. To find the top K documents efficiently, this becomes a maximum inner product search problem, solved approximately in sublinear time using FACE with hierarchical navigable small world graphs. Second, the generator. This is BART large, a denoising autoregressive transformer with 400 million parameters. To condition BART on both the input and retrieved documents, they simply concatenate the input query X with each retrieved passage Z and feed this concatenation into BART's encoder. The key architectural decision is treating retrieved documents as latent variables. You don't need explicit supervision telling the model which documents to retrieve. Instead, you marginalize over the top K retrieved documents, letting the gradient signal from the final task loss propagate back through the retrieval distribution. The paper proposes two distinct formulations that differ in how they marginalize over retrieved documents. RAG sequence treats each retrieved document as a single latent variable for the entire output sequence. The probability of generating output Y given input X is approximated by summing over the top K documents. For each document Z, multiply the retrieval probability P eta of Z given X by the full sequence generation probability P theta of Y given X and Z. This means each candidate answer is generated entirely conditioned on a single document. RAG token, by contrast, allows the model to draw on different documents for different tokens. Here, you marginalize at each token position independently. The probability of the full sequence is the product over tokens, where each token's probability is the sum over documents of the retrieval probability times the generation probability. This is more flexible, allowing the model to synthesize information from multiple documents within a single generated sequence, which proves especially powerful for tasks like Jeopardy question generation. Training is elegantly simple. Given input-output pairs, you minimize the negative marginal log likelihood of each target using Atom. A critical design choice. They do not update the document encoder during training. Updating BERT-D would require periodically re-encoding and re-indexing all 21 million documents, as Realm does. Instead, they fix the document encoder and index, only fine-tuning the query encoder BERT-Q and the BART generator. This makes training dramatically more practical. Decoding differs between the two models. For RAG token, the marginalized per-token probability acts as a standard autoregressive transition, so you can plug it directly into beam search. For RAG sequence, things get more interesting. Since the likelihood doesn't decompose into per-token terms, you can't use a single beam search. Instead, you run separate beam searches for each of the K-retrieved documents, collect all hypotheses into a candidate set Y, and then score each hypothesis by running additional forward passes for documents where that hypothesis wasn't in the beam. This is called thorough decoding. For efficiency, they also propose fast decoding, which approximates the probability as 0 for any hypothesis not generated in a document's beam. Now for the results, and they're striking. On open domain question answering, RAG sets new state-of-the-art on natural questions at 44.5 exact match, trivia QA at 56.8, web questions at 45.5, and curated Trek at 52.2. What makes this remarkable is the comparison landscape. The closed book baseline, T5 with 11 billion parameters, scores only 34.5 on natural questions. Even T5 plus salient span masking, a specialized pre-training objective, only reaches 36.6. RAG achieves 44.5 with just 626 million trainable parameters, about 18 times fewer. On the open book side, RAG outperforms DPR, which uses a more complex pipeline with a BART cross-encoder re-ranker and an extractive reader. RAG demonstrates that you need neither a re-ranker nor an extractive reader. Perhaps the most telling result, RAG achieves 11.8% accuracy on natural questions, even when the correct answer doesn't appear in any retrieved document. An extractive model would score exactly 0 in this scenario. The parametric memory fills the gap. Beyond extractive QA, RAG excels at generation tasks. On MS Marco Abstractive QA, RAG sequence outperforms BART by 2.6 blue and 2.6 rouge L points, approaching the state-of-the-art, which has access to gold passages. For Jeopardy question generation, human evaluators found RAG more factual than BART in 42.7% of cases, while BART was more factual in only 7.1%. RAG was also judged more specific by a wide margin. Crucially, RAG generates more diverse outputs. Measuring the ratio of distinct trigrams to total trigrams, RAG sequence achieves 53.8% on Jeopardy generation versus BART's 32.4%, without any diversity-promoting decoding tricks. On fever fact verification, RAG scores within 4.3% of state-of-the-art pipeline systems, which use domain-specific architectures, substantial engineering, and intermediate retrieval supervision. RAG uses none of these. The top retrieved document matches the gold evidence article 71% of the time, and a gold article appears in the top 10 in 90% of cases. One of the paper's most fascinating analyses is the document posterior visualization. Consider the Jeopardy prompt Hemingway. RAG token retrieves 5 documents and generates The Sun Also Rises is a novel by this author of A Farewell to Arms. The document posterior reveals something remarkable. When generating the token Sun, document 2, which discusses The Sun Also Rises, dominates the posterior. When generating Farewell, document 1, about A Farewell to Arms, takes over. But here's the key insight. After the first token of each book title is generated, the document posterior flattens. The generator no longer needs the documents to complete the title. It already knows the titles from its parametric memory. The non-parametric retrieval guides the generation toward the right factual content, and then the parametric memory takes over to complete the fluent output. This is the essence of RAG. The two memory systems aren't redundant, they're complementary. The ablation studies reveal what actually drives RAG's performance. First, learned retrieval versus frozen retrieval. When you freeze the retriever during training, performance tops across the board, confirming that end-to-end retrieval learning is essential. Second, dense retrieval versus BM25. Replacing the learned dense retriever with a traditional word overlap BM25 retriever hurts performance on most tasks, with one exception. On fever fact verification, BM25 actually outperforms dense retrieval, likely because fever claims are heavily entity-centric, favoring exact lexical matching. On open domain QA, learned dense retrieval is critical. Third, the effect of retrieving more documents at test time. For RAG sequence, performance on natural questions monotonically increases with more retrieved documents. For RAG token, performance peaks around 10 documents and then plateaus. This makes intuitive sense. RAG sequence benefits from having more candidates to marginalize over, while RAG token already mixes information across documents per token. Perhaps the most practically significant result is index hot swapping. Because RAG's knowledge lives in an explicit, non-parametric index rather than frozen parameters, you can update it simply by swapping the index, with zero retraining. To demonstrate this, the authors built two Wikipedia indexes, one from December 2016 and one from December 2018. They prepared 82 questions about world leaders who changed between those dates. With the 2016 index and 2016 ground truth, RAG answers 70%. This paper's impact cannot be overstated. RAG established the template for how the entire field now thinks about grounding language models in external knowledge. The core idea: treat retrieval as a differentiable latent variable and marginalize over retrieved documents, has been adopted and extended by virtually every major retrieval-augmented system since. The paper crystallized the key design dimensions that subsequent work explores: what to retrieve, how to retrieve it, when to retrieve during generation, and how to combine retrieval with generation. With 626 million trainable parameters, RAG outperformed T5's 11 billion parameter closed book approach, demonstrating that architectural innovation, not just scale, drives capability. The paper remains essential reading for anyone working on knowledge-grounded generation, fact verification, or open domain question answering.